diffraction by a circular aperture by M.K. Srivastava, Department of Physics, Indian Institute of Technology, Roorkee, Uttarakhand. In the last 3 lectures on diffraction, we have studied the meaning of diffraction, what is meant by it, the difference between Fresnel and Fraunhofer laws of diffractions. We have studied Fraunhofer laws of diffraction from a single slit, a pair of slits and a grating. We have studied the concept of resolution. In this lecture, which is the last one on diffraction, we shall study Fraunhofer diffraction at a circular aperture in some detail. See, it is an effect of great practical significance in the study of optical instrumentation. Because of this, we would like to spend a little more time on it. See, imagine a typical arrangement, plane waves impinging on a screen capital sigma containing a circular aperture and the consequent far field diffraction pattern is spread across a distant observing screen sigma. By using a focusing lens, we can bring the observing screen sigma close to the aperture without changing the pattern. The screen is still virtually at infinity, not really infinity, but practically a very large distance away from the aperture. Now, if L is positioned within and exactly fills the refracting opening, that is completely fills the aperture, the form of the pattern is essentially unaltered by the lens. It is really controlled by the aperture. The light wave reaching this screen is cropped, means is obstructed, so that only a circular segment propagates through the lens, that is through the aperture, to form an image in the focal plane of the lens. This is obviously the same process that takes place in an eye, a telescope, microscope or camera lens, or practically in any optical instrument. The image of a distant point source as formed by a perfectly aberration free converging lens is never a point, but rather some sort of a diffraction pattern. We are essentially collecting only a fraction of the incident wave front, one that passes through the aperture. Most of it is obstructed, and therefore, we cannot hope to form a perfect image. Consider the configurations shown. A monochromatic plane wave propagating in the x direction is incident on the opaque diffracting screen capital sigma. Remember, this is a plane wave we are considering. We wish to find the consequent far field flux density distribution in a space or equivalently at some point p. Let us consider few things here. The opaque screen is in the yz plane, x axis is perpendicular to the plane, O is the origin of the coordinates. We are finding out the intensity distribution, say find out intensity at some point p. The point p has coordinates capital X, capital Y, capital Z. Capital R is the distance of this point from the origin of coordinates. The small x for the aperture is 0, it has only dimensions along y and z. any differential area ds within the aperture may be taken as being covered with coherent secondary point sources, individual sources, sourcelets really, where the differential area ds is much smaller in extent than is lambda, so that all the contributions at P remain in phase and therefore interfere constructively. This is true regardless of the angle theta. ds emits a spherical wave. Now, if E0 is the source strength per unit area, then the optical disturbance at the point P due to a small elementary area ds in the aperture is given by E naught upon r. This r in the denominator is because of it is a spherical wave, and e raised to the power I omega t minus k r, that is the usual wave phase factor times the area ds. You see, the source strength is assumed to be constant over the entire aperture. The reason for this is because the incident wave front is that of a plane wave front, which leads to a uniform intensity pattern on the surface of the aperture. Now, the distance ds from ds to point P naturally is given by this expression. Small y is not appearing, small x is not appearing here because that is 0 for the plane of aperture. So, this is the distance capital X square plus capital Y minus y square plus capital Z minus Z square whole raised to the power half. If Fraunhofer diffraction condition occurs, we know this distance must approach infinity, must be very large. In the present case, it would be very large compared to the size of the aperture. Now, in the amplitude term, we may replace small r by the distance OP. The distance OP, the distance of the point P from the center of the aperture. Okay. So, we can replace small r by capital R as long as the aperture is relatively small, and it is really small compared to small r or capital R. So, this we can approximation can be made in the amplitude term. However, in the phase term, we need to be a bit more careful. The reason is you have k into small r, k r appearing there, and k is pretty large, k is 2 pi by lambda, lambda is a small number. So, for the phase term, we expand the small r, okay, write it as capital X square, capital Y square plus capital Z square, then we have plus y square plus z square and minus twice capital Y small y plus capital Z small z whole square root. Capital X square plus capital Y square plus capital Z square gives me capital R square. So, we take R common outside within the square brackets, then we have 1 plus a term y square plus z square upon r square, and the last term which is minus twice of y plus z upon r square whole square root. We drop the second term which is y square plus z square. These are very small numbers. They are controlled by the size of the aperture, and we know the size of the aperture is very small compared to capital R. So, we drop this term. The result is small r is now equal to capital R and then 1 minus twice y plus z upon r square, the whole square root. Now, expanded through binomial expansion, so that whole square root factor drops down, and now we have finally capital R multiplied by 1 minus this term y plus z upon r square. Now, in the above, as I pointed out earlier, we have ignored the term y square plus z square upon r square. As in the far field case in which we are interested, r is very large in comparison to the dimensions of the aperture and have taken the binomial expansion retaining only the first two terms. Now, using this expression for the disturbance at P and then integrating it over the aperture to get the full contribution. So, we get for the total disturbance arriving at the point P, E is equal to E naught into the usual wave phase factor e raised to the power I omega t minus k capital R now here divided by R, and then integration over the aperture, which is a two dimensional integration. The integrand is e raised to the power I k y y plus z z divided by R to be integrated over the whole area of the aperture. Now, as the opening here is circular, we use cylindrical coordinates in both the plane of the aperture and the plane of observation. For small y and small z in the aperture, we use rho and phi, and here for the point P where the intensity is to be calculated, for capital Y and capital Z, we use Q and capital Phi. So, now the small z is equal to rho cos phi, small y is rho sin phi, capital Z and capital Y, these are for the point P, capital Z is equal to Q cos capital Phi and capital Y is equal to Q times sin of capital Phi. The differential area ds, which was dy dz, now is d rho and rho d phi. So, rho d phi. Substituting these expressions in the expression for the electric field, for the strength of the disturbance, E is now equal to E naught times the phase factor as before, e raised to the power I omega t minus k capital R divided by R. Remember again, the division by R is because the disturbance is a spherical wave. To be integrated now over rho, the range is 0 to A is the radius of the aperture, and over phi making one complete round. So, phi varies from 0 to 2 pi. The integrand is e raised to the power I k rho q divided by R, and whole of this factor times cos of phi minus capital Phi rho d phi. So, this is the expression we have. This is to be evaluated. This is in the cylindrical coordinates, which are naturally appropriate for this problem. Now, this problem has a complete axial symmetry. I mean symmetry about the x axis, which is perpendicular to the aperture, and therefore, the final solution must be independent of phi. The capital Phi does not mean anything. It cannot affect the final solution because of the symmetry about the x axis. We may choose it conveniently, might just as well solve the above expression taking capital Phi equal to 0. So, we do that, and thus the expression now becomes E is equal to the E naught into the phase factor is the same thing as before divided by R, no change, integration over A from 0 to A, integration over phi 0 to 2 pi as before. The only change here is that e raised to the power I k rho q divided by R times cos phi in place of cos of phi minus capital Phi, rho d rho d phi. Now, let us consider this is the double integral over rho and phi. Let us consider the integration over phi. 0 to 2 pi, one complete round, e raised to the power I k rho q divided by r, this factor times cos phi d phi. Now, this double integral which appears in the expression for E, this is the defining relation for the Bessel function. Bessel functions of the first kind and of 0 order. This integral is equal to 2 pi times j0, j0 means of the order 0, and the argument of the Bessel function is k rho q divided by r. So, we substituted this back in the expression for E. So, the total disturbance reaching the point P now becomes, phi integration has already been done. So, now the expression is E is equal to E naught, the usual phase factor divided by r, 2 pi, and the integral from over rho from 0 to a, the integral is now over j0 argument k rho q upon r rho d rho. So, now the integral over rho is to be performed. To do that, we change the variable rho to say w equal to k rho q upon r in the integral. So, this integral from 0 to a j0 k rho q upon r rho d rho now becomes r upon k q squared integral over w now. So, 0 to w equal to k a q upon capital R, the integrand is j0 w w dw. This again can be carried out. The result of this integration is there in the second line. So, we get r upon k q squared, and the result of integration is k a q upon r times j 1 of k a q upon r. J 1 is again Bessel function of the first kind of order 1. Now, we rearrange the variables outside the Bessel function. So, it can be written as a square, remember a is the radius of the circular aperture. So, a square times r upon k a q times j 1 of k a q upon r. You see, in this derivation integrating over j 0, we have used the recurrence relation of a Bessel function. We have invoked properties of the Bessel function. We shall not go into really into the details of these recurrence relations. All right. Using this expression for E, now we have E is equal to E naught E of I omega t minus k r as before divided by r multiplied by 2 pi a naught a square into r upon k a q into j 1 of k a q upon r. Remember, this pi a square is the area of the aperture. Now, let us spend some time on Bessel function. We shall not go into the real details of these functions. It is enough if we just appreciate that they are just like sine and cosine functions. The difference is they are slowly decreasing like damped oscillatory functions. This shows a graphical representation of the various Bessel functions. J 0 of u, u is the argument as a function of u, j 1 of u, j 2 of u. The main feature which should be noted is that these are oscillatory functions. Damped oscillatory, the amplitude goes on decreasing, and j 0 is equal to 1 at 0 argument at u is equal to 0, while higher order ones they all vanish at u equal to 0. So, now using all this, let us calculate the intensity at the point P. Naturally, the intensity is given by E into complex conjugate of E divided by 2, that is a very standard expression. So, we get for the intensity at the point P is 2 E naught square A is capital A square. Remember, capital A is the area divided by R square times the square of this combination J 1 of K A Q upon R divided by K A Q upon R, the expression for the intensity. One thing you should note here, this is a cylindrical symmetry. So, the position of the point P on the screen is really defined by Q. Q is sort of a radial distance on the screen. Everything else is fixed, R is taken care by the distance of the screen, A takes care of the size, K is 2 pi by lambda determined by the wavelength, capital A is the area, and E naught square depends on the intensity of the incident wave. So, this is really a function of the radial distance on the screen of the point P determined by Q. Now, to find the intensity at the center of the pattern, that is corresponding to Q is equal to 0, which means the argument of Bessel function will be 0. We again use the property of Bessel function. We know J 1 of u goes to 0, but J 1 of u upon u goes to half. So, we can use this to obtain the intensity at the point P 0, that is in the exactly in the forward direction. That intensity is given by E naught square capital A square, capital A remember is the area divided by 2 R square. So, let us substitute this expression. Finally, the intensity now appears in this form, I is equal to I naught twice J 1 of K A Q upon R divided by the factor K A Q upon R, and whole thing is squared. Now, sin theta, remember that. So, that is Q over R. So, we can also write it in terms of sin theta. So, the above expression can be written in this form as a function of theta is equal to I 0 and the square of this quantity twice of J 1 K A sin theta upon K A sin theta. If you remember, this expression is very close to what one has in a rectangular single slit. There the expression comes out to be in the form of some sin beta upon beta. Beta is some function like this. In place of sin beta over beta, we have J 1 of beta over beta. I mean, that is the qualitative change in the expression when the rectangular slit, thin slit basically changes into a circular aperture. Now, let us study this expression. The intensity is maximum as theta equal to 0. Now, the central disk, this is surrounded by, why I am calling it a disk? Because of the symmetry about the x axis. So, the central disk is surrounded by a dark ring that corresponds to the first 0 of the Bessel function J 1 K A sin theta, and this 0 occurs when the argument K A sin theta is equal to 3.832. The radius q 1 drawn to the center of this first dark ring can be thought of as the radius of the central disk, the size of the central disk, extent of the central disk. Let us calculate this q 1. So, q 1 is equal to r sin theta. I divided it multiplied by K A. Ka sin theta, I put the value 3.832 for the first 0 of J1 multiplied by R upon Ka. K is 2 pi by lambda. So, I have that expression. Now, 3.83 divided by pi, that gives me 1.22. So, 1.22 or lambda by 2a. 2a is the diameter of the aperture. For a lens focused on the screen, the focal length will replace R. So, if a lens has been used, then in that case Q1 will be given by 1.22 f lambda by d. As I said, d is the diameter of the aperture. Now, the important result here is the radius Q1 of the central disc, which is the most important, varies inversely with the whole diameter. That is the important result. Now, the higher order zeros of the Bessel function, which will lead to rings around the central disc. They are given by when Ka sin theta, which is equal to Kaq upon R, other values are 7.02. You see, first 0 was at 3.382, the expression that we had just now. But then the other next 0 is at 7.02, 10.17 and like this. If we divide these by pi, then they correspond to the values 2.23, 3.24. Remember, in the first case it was 1.22. Now, when these minima are there corresponding to zeros of the Bessel functions, in between there will be secondary maxima. Naturally, they are located where the argument K sin theta satisfies this condition. You see, the intensity depends on J1 u upon u. So, its derivative, put it equal to 0, get the value of u, and when this calculation is done, the K sin theta comes out to be equal to 5.14. So, remember, you had the first 0, then a maximum at 5.14, minimum at 7.02, again a maximum at 8.42, minimum at 10.17, a maximum at 11.6 and so on. Now, the value of I upon I 0, that is the interesting thing. It drops from 1 at the central point, that is the important thing. The central maxima, if we take its intensity as 1, then relative to that, the intensity of the first the secondary maxima away from the central one, that is the intensity in the first ring, is 0.0175, much less. In the second ring, 0.0042 is still smaller. In the third ring, 0.0016, very small compared to the central disc. So, basically in actual practice, what we will observe a pretty bright central disc whose radius is determined by the diffraction pattern, and that factor comes out 1.22. That is the important factor. And then there is a dramatic fall in intensity. The rings are very poor there, but calculation shows that about 84% of the total energy is contained within the central disc. Here we have a plot. You see this on the right side, this towering central maximum corresponds to the higher radiance circular spot carrying an intense total energy content of 84%. Then it shows a ring, second ring. On the left we have a graphical picture showing the intensity of the central maxima, and relative to that we get a minimum at 3.83, then we get another minimum at 7.02, really 7.016. In between there is a maximum similarly a maximum. So, this sort of picture is there, but the essential feature is we can forget about the rings. The main thing is the central disk carrying most of the energy and the radius of this central disk, which is important. This picture shows for a aperture diameter of 0.5 millimeter hole, a pattern will appear like this. For a 1 millimeter hole diameter, the main thing is as d approaches lambda, remember as d becomes very small, the central disk can become very large indeed, and the circular aperture begins to resemble a point source of a spherical wave coming out in all directions. So, the size of the disk becomes infinite essentially. See, the finite size of the central disk, this is called a airy disk and is responsible for the limitation on the resolving power of all the optical instruments. You see, it is an effect of the wave nature of light, and as we have seen, it has nothing to do with the instrumental inadequacy. Even if we have perfect optics, all the lenses completely aberration free, monochromatic aberration as well as chromatic aberration, everything, even then the size of this, the airy disk will be there, and its size, its radius will depend on the aperture of the aperture in the screen, or basically on the size of the lens. So, that is the basic result, and this is coming out because of the wave nature of light. It is a basic diffraction effect. Okay, so I hope this discussion will help in understanding the concept of resolving power, limit of resolution, and possible steps to improve the resolving power of any optical instrument. Thank you.